So namely, when the field becomes much larger than the arc length over the thickness of my sample, you can basically ignore the arc part of the orbit, and the orbit is roughly just the electron bouncing these finite size levels, bouncing back and forth across the sample, and I get no longer periodic structure with magnetic field, so the quantum oscillation cease. So these quantum oscillations and their kind of characteristic thickness dependence give me an experimental signature of this bulk boundary correspondence in this material, and the fact that the surface arcs are topologically tied to this bulk chiral lambda level. And you can reveal it in various ways. One simple, at least as a theorist way, is to imagine just changing the magnetic field orientation and tracking the position of these peaks in the density of states. And you see that there's a part that depends on the angle of the field, but actually the thickness-dependent part will not depend on the field. And so this thickness-dependent kind of offset of the phase of these quantum oscillations, if you can track it precisely, in principle reveals the fact that you have this orbit that goes through the bulk. So it's kind of like a way to measure the topology of these orbits. And so one thing, as we move towards the kind of experimental part of the discussion, is that one important practical consideration always in quantum oscillation measurements is disorder. And in particular, you need to be able to complete the orbit without substantial scattering that will dephase the orbit if you want to get coherent quantum signatures out of it. So fortunately, in a lot of these direct materials, the mean free path can be actually very long, and the scattering times, be it quantum or transport times, are very long. And I'll say a bit more about this once we get to the experimental part. And yeah, just to kind of recap something Sid was mentioning, is that a related measurement is to look at cyclotron resonances associated with these orbits. It's basically the same story, but here if I drive in a field with some kind of electromagnetic wave, the electric field can kind of resonantly drive these orbits if you choose the right frequency. And the cyclotron frequency will also saturate at large fields, and this saturation frequency is dependent on the thickness of your sample. And moreover, you can see that there's a polarization dependence. If I drive perpendicular to the arc, the electrons on the arc can absorb energy from the field, but the electric field is along their velocity. But if I put the electric polarization this way, they won't absorb very much energy, so there should be a characteristic polarization versus arc orientation dependence. Yeah, and it's kind of tantalizingly mentioned there's a cute trick of making a very surface-sensitive probe out of this, which I guess you'll have to ask in a moment. All right. So with this kind of simple semi-classical theory of these Fermi arc quantum oscillations in hand, I want to turn to some recent data measured in James Analytis' group, and the postdoc really championing this measurement is Philip Moll, who will be moving to faculty position in the MPI in Dresden in October. So they developed this really cool way to make microstructures out of cadmium arsenide, and this picture is a bit hard and has some optical illusion-like elements to it, so let me walk you through it. So what they do is they start with a thin film of cadmium arsenide, and they take a focused ion beam, and they can basically carve out sections that they don't want. And so these dark shaded sections are pieces that they've carved out with a focused ion beam, and you can see that they leave in these holes a thin film of cadmium arsenide kind of standing on its side compared to the pictures I've been drawing so far. So these little purple sheets are thin films standing on their side. And they can control the thickness of this kind of freestanding membrane piece and also its geometry just by changing kind of the angles of the fabrication, the ion beam milling So the nice thing about this fabrication technique is that the ions are incident from the top. So they're actually come in at grazing incidents to the surface. They have the effect of actually cleaning off the surface as they come down. So that any kind of junk sticking out will get blasted off. They get very nice surfaces on these side surfaces. The top surface is junk, but in the way they've fabricated it, this is not the important surface for surface state. And the other nice thing is that both surfaces have basically the same fabrication parameters, and so they'll be roughly the same. Okay, so the measurement they do is to run current through these devices in a field. And so let me start with the field. You can orient the field in any angle you like. And if the field is perpendicular to the surface, so that's 0 degrees, you see this large transverse magnetoresistance that's characteristic of these materials, and on top of it some quantum oscillations, which if you analyze, you see two frequencies, say this first peak and the second peak, which has some weird stretched line shape. And if I turn the field parallel to the surface, I only see one frequency. So these little double peaks here are actually spin splitting of the bulk from the surface. But if I Fourier transform, I can clearly see just one bulk, so one frequency. And moreover, as I change the angle of the field continuously, I can watch what happens to these two peaks. And this one that I'm calling FS has some characteristic 1 over cosine theta dependence, which clearly marks it as a surface state. And the bulk, this blue peak, is actually a bulk pocket that's roughly symmetric. And so this is really characteristic or suggestively depicted in this polar plot, where here is an angle. The polar plot is the frequency versus angle. So the question is, what's the source of this surface signal? Is it related to the while oscillations that I was talking about in the first half of the talk? And to do this, I have to address the elephant in the room, which is related to Youngbeck's question, which is, so cadmium arsenide is actually a Dirac semimetal, it's not a Weil semimetal. So what is the role of this crystal symmetry requirements in the protection, and how does surface states of one of these Dirac semimetals work? So naively, if we picture Dirac semimetal as two copies of Weil semimetal protected by crystal symmetry, you expect two sets of arcs. One from the one kind of crystal symmetry representation and one from the other, expressed in the opposite way. And generically they'll meet at the bulk Dirac point. The problem is that the crystal symmetry protecting the bulk nodes is actually some rotation symmetry along the axis separating them. So any surface that you expect to see these arcs actually doesn't preserve this symmetry. So you might think that this is immediately game over for these arcs, and that they'll reconstruct into some kind of more conventional looking surface state. So the situation is actually a bit more subtle. So as the arcs approach the bulk where they come close to each other, they're actually retreating into the bulk of the sample. And so this crystal symmetry breaking, which is only active at the surface, is becoming less and less effective. And so actually this corner feature that I've drawn here exists over some finite range of surface parameters. And if the surface symmetry breaking is sufficiently strong, but there's some finite strength required, it can reconstruct into this kind of surface state. But as she was mentioning, there's an important topological constraint on the existence of surface state. And you can roughly think of it as the way we get this Dirac semimetals by inverting some S and P bands. And they'll cross in some ring. And since it's a spin-orbit coupled system, this ring will be lifted almost everywhere except due to this axial rotation symmetry, which keeps 2 points here. But up to this last part of the sentence, everything I told you is a recipe for a topological insulator. And you can convince yourself that actually the topological invariant that you get by this band inversion is not affected by just having symmetric gapless points on the edge, but there actually will be a topological insulator kind of surface state. And the thing is that it may or may not intersect the nodes, but when it does, it kind of sticks to the bulk Dirac nodes over some finite range of parameters. And additionally, you can see that if you start with this Pi-like surface termination, a dope. Eventually the TI surface will run into the bulk Fermi pockets, and I'll get this arc kind of termination instead. So it's very relevant to think about Fermi arcs in this system. So there are basically three origins for this surface, three possible origins for this surface space. The one is this arc-like termination, where the surface states run into the bulk pockets and not into each other. And there we would expect some wild-like quantum oscillations. Another possibility is this just having an ordinary 2D, well, almost ordinary, but helical TI-like surface state. And the last is that if the chemical potential is, say, up above this Dirac region, then